What time does this go till?
It's 5:30 to 6:50, but it's completely optional, so you're free to leave at any time, and it will be recorded. And usually I post it the same night, but sometimes I don't post it till the next morning.
Okay, because yeah, I got the lab tonight in Virginia Beach, so I gotta leave at 6.
Yeah, there are locations on campus in case you want to go there where you could actually watch this anyways, and then you wouldn't have to cut it so short. You might give that a try for the next class, but it's completely up to you, bud.
Okay. Yeah, I hadn't thought of that. Thank you.
Yeah, we have the labs are available as well as at the end of our hall at the Virginia Beach building. There's a series of computers at the end of the hall that pretty much everybody's supposed to use, are allowed to use, but it really is belongs to chemistry. But if they're not busy, you're welcome to use them.
Okay, cool. Thank you.
You're welcome. See a couple names I recognize. Should be starting in a few minutes, but I'm waiting for a few more people to get here just in case. Got almost all of us here. All right. So first, while a good fraction of you guys are here, looks like about 9 out of 15 of you are here. I think one person was suggesting they were going to drop, so it might even be 9 out of 14. But this will be recorded as well, and nobody's actually required to attend. Uh, if I found that you guys actually had a better time that worked, I would be glad to consider moving it. I think I'll send out an email to question you guys and see how many people could possibly attend at this hour versus 11 a.m. on Thursday and Tuesday or something like that. I suspect most people won't be able to do it on Tuesday and Thursday, 11 a.m. But just in case, I'm going to ask and see if anybody needs that as an option instead. Basically, I'm going to plan on going with whichever one the most people can make it to, and it looks like I got 11 of you guys in here already, so that's a really good sign that we'll keep this date. I just sent out a couple of emails today too. To let you guys know, I finally got the syllabus updated. I had some problems associated with the Canvas website importing stuff, so I couldn't even create your Pearson page, but that's now done and working. So you can now go, for instance, to Module 1, which is for week 1 from January 13th to January 19th, and you can click on one of those homework links and it'll take you right to the homework assignment. Homework assignments in general always going to be due. I think I accidentally in the text message I just sent to you guys, or to the announcement I just sent to you guys, I think I accidentally left the data in there from my Monday Wednesday class. But what I did do was normally your homeworks will be due not on Sunday, as I said, that's for Monday Wednesday classes, but will be due on Mondays at 11:59 p.m. However, because I had a little bit of delay getting things started, I went ahead and pushed this first assignment back to Thursday of next week, which would be the 22nd, I believe. So, of course, you never, ever, ever want to trust the dates that it says on Canvas regarding your Pearson homeworks, because I've seen that it seems almost random numbers and random dates that get put on Canvas for due dates for Pearson assignments. So just never trust that. I'm going to try to work this semester at a rate of a little bit more than one chapter per week. That means that we should have a chapter worth of assignments every Monday due at 11:59 p.m. So try to get used to that, even though this first assignment I pushed back till Sunday. If they're chapters other than chapters 17 through 31, they're probably going to be extra credit. Ideally, I get to go past chapter 31 and I'll do 37, 38, 39, and then I'll do the nuclear physics chapter and then I'll do the cosmology chapter. But I haven't been able to make it that far for a while. So pretty much if we're only going to cover 17 through 30, 17 through 31. Any homework assignments or any Pearson assignments you see for chapters other than that, even if they don't have parenthesis EC or EC in it or extra credit written in it, they're going to be extra credit. Okay, so just keep that in mind. I do ask my students to chat me your first and last name just when you get here so I can have a sort of a roll. Additionally, I want to remind everybody it's on the syllabus, but y'all might not have seen it, and I try to say it on video too, and I didn't say it on video last night. But if you have any problems with your name or face appearing on the internet, specifically, this video, when I finish lecturing slash covering material for you guys, I'll be saving it as a MPEG and then uploading it to my YouTube channel where everybody can access it. It's completely open. So if you guys are trying to not let somebody find you, or maybe you're in witness protection or something like that, then you might want to go ahead and change your username within Zoom to something innocuous. You can maybe, do some letters and initials, or initials for your first and last name or something, so that I might be better able to figure out who it is. But the main thing is, if you're chatting me your first and last name when you get here, I know who's going to be here. So just feel free to change your username in Zoom to something else, and you might also never share your camera view. Additionally, and here's the last part, if you do have a problem where you can't have your name or image put on the internet, I need you to send me a message saying that, telling me exactly your first and last name, as well as what class you're in, PHY 241 D01B or 242 005B, which is what you guys are in, or whatever, and just tell me whether that you can't be seen, and I will make a note and I'll edit it always out before I'll always edit it out before I post them online. I haven't had anybody needed to do that yet, but I always want to give that an option. I know people have sordid lives and things that can get a little hairy, so I don't want to get anybody in any trouble. By the way, I should probably introduce myself. I'm Mr. Younger. I teach physics and astronomy and mathematics here at TCC. Actually, I haven't taught math yet, but I've been approved for teaching math. I've mostly been teaching the calculus-based physics for the last several years, and occasionally an algebra-based or an intro or a conceptual physics class. But this is sort of my forte. I take some pride in the ability to teach what I think is probably the most rigorous, most complex course that TCC offers, and I try to do it in such a way that everybody can understand. And this Physics 242 is that course. Okay, you're going to learn and use a lot of mathematics that, in some cases, people with bachelor's degrees in mathematics have never seen. In some cases, people with master's degrees in mathematics haven't seen it. But normally those are mathematics master's degrees where their degree is actually in math education as opposed to math. Anyways, but that's what this course is about. We're going to start off with basically electrodynamics is what we used to start with. We now start with more or less something like thermodynamics, and then we go, after we finish 4 chapters of thermodynamic type material and kinetic theory and all that stuff. Then we go into electrodynamics, and then if time allows us, we get out of electrodynamics and go to quantum mechanics, and then we go to nuclear physics, and then maybe even cosmology. But like I said, I haven't been able to get to cosmology in forever. Uh, Actually, I don't think I've ever been able to get to cosmology, but I have gotten to nuclear physics before. So, anybody have any questions before we get started? All right, I am going to tell you, I'm not going to cover our syllabus very much. I'm going to make a single video that, because my syllabuses for all 4 of my classes are exactly the same. The only difference is being, some of them are for 241, so they have different schedules, and other ones are for 242. Uh, my daughter calls me every day at this time, knowing darn good well that I teach a class at this time. Anyways, but now I done forgot what I was saying. Mm, lectures will be. Someone asked how long after the live lectures will the recordings be available? I usually try to make them within 20, 30 minutes after the video, after the lecture's finished. But sometimes I'm unable to do it till the morning. It all depends on how much bandwidth I've got when I'm trying to upload the video and download the video. So that should be where when it comes up. So if you go to my YouTube channel, which I do recommend, if you go there and subscribe to it, it'll actually send you a text message or an email every time something new is posted, and it normally includes the title. So you can normally look at the title and tell whether it's for 241 or 242 because the subject matter is so distinctly different. Let me give you that since people are asking, let me type that real quick exactly what my YouTube channel is www.youtube.com/at physics PHYSICS solutions. Whoa, Nelly, my mouse just jumped to the wrong place. Solutions dot spelled out com spelled out. So that is my actual YouTube channel, and you can get that. There's thousands of hours of lectures in there. Some of them are summer lectures, so they even will last like 3.5 hours in a couple cases. You obviously probably don't want to watch that. My oldest daughter uses those to fall asleep by, so. Yeah, I can tell you it must be awesome. But anyways, I'm also going to let you know my email address. I don't want to put that out over the internet because I'll get all sorts of spam and I already get enough of that. But there's my email address. The big thing is when you email me, my syllabus tells you explicitly you have to, one, only email me from your TCC account. Two, always start the subject line of your email with 242 space night. Okay. Or I think I put it on my syllabus as 242 space online. Either one of those is acceptable, not as long as it has 242 and then it tells me whether it's night or online or day or something like that. 241 space online is fine, or 241 space night is fine. Uh, Additionally, I usually give my students my phone number, and obviously, I definitely don't want to put that out on the internet. So I'm going to type it again in a chat. And the reason why is because I get on the order of 250 emails a day, and there's some chance that I might miss your email. And if you send me an email and don't get a reply within one business day, and my syllabus explains what one business day is, but if you don't get a reply within one business day, I recommend that you first check the announcements on Canvas, which every time I post an announcement on Canvas, it's supposed to email you as well. But either way, make sure you check the announcement on Canvas as well as your personal email and see if perchance I sent an email to everybody that happened to address your question. Because what often happens is I'll get an email where a student asks a question, but then I'll look and there's like 15 emails and the students all ask the same question. So rather than reply to each of you individually, I post a single email to the whole class about that question. So check that out. But if you don't get that email from me, either generically to everybody or specifically to you, then that's a perfect time to contact me via text message. I don't recommend you calling me. I don't answer numbers that I don't know, so you would ideally want to text me. And then if we need to talk, I'll say talk and I'll change my phone setting where I can actually answer the phone. But I want to remind you that when you do text me, I want you to include your first and last name every time you text me, as well as, I mean, if we're talking like in real time, like you text me, I reply, and then you text me back that quick, then no, you don't have to repeat it every time. But if even 10 minutes has gone by, you need to put your first and last name and tell me what class you're with every time you text message me, because otherwise I have to go through every text message you ever seen me. And sometimes I have students that I've been talking to for 4 or 5 years, so it takes a really long time to go through all those text messages to find the name of the student. So make sure you do that. As I said, the rest of the syllabus I'll discuss on a video that I make. So I want to go ahead and get started covering the material with you guys. So let me start by sharing my computer screen, or technically my iPad screen with you guys. Oops. Hold on a second. Let me not do that yet because I just realized that my iPad shut down and it's not doing what it's supposed to do yet. So let's see what I can do real quick and see if I can fix that. In the meantime, what I'm going to do is share my computer screen with you and show you specifically the photograph that you see in the opening page of the chapter we're covering. So here it is. So you can see the chapter we're covering is chapter 17. That's what we're starting off with. And as you'll see in your Pearson website, I think it's chapter 14, 15, and 16 are already up and available, but they're extra credits. Those 14 and 15 are chapters you should have covered in the equivalent of 241. Chapter 16 is just a good chapter that might be interesting, so I give you all the opportunity to do that by extra credit. But the main thing is I want to make sure you guys uh, not crap. Done lost my train of thought again. Oops, that helps. So the main thing is I just want to make sure you guys can access the textbook and all that good stuff. Here's the temperature, thermal expansion, and the ideal gas law. That's the name of this chapter 17. Oh yeah, I was talking about chapter 16. But like I said, I do online homeworks that count as extra credit. You can look at the syllabus to figure out how they are actually covered. Uh, what I'm going to tell you is in chapter 17, the contents are section 17.1, the atomic theory of matter. That's actually something that's going to be kind of a introduction to basically, the idea that matter is made up of atoms slash molecules. Then we're going on to section 17.2, which is temperature and thermometers. Section 3 is thermal equilibrium and the zeroth law of thermodynamics. I want to give you guys a warning whenever you see, at least in physics, but I'd say probably in physics, chemistry, biology, all your sciences, and maybe some other subjects. But when you see a chapter or a whole subsection of a chapter devoted to some big law or principle, or specifically something that says law in it, you should probably go ahead and commit that to memory because us teachers often think that we give you little breaks by just taking, for instance, and asking you to state verbatim what is the zeroth law of thermodynamics. Uh, those are all supposed to be gifts from us, but inevitably, when we give them to you, students on the order of 50% or so will get them wrong. And it's terrible because, we're trying to give you free points and give you a little bit of confidence doing your test, but you don't get it that you're supposed to know these things. So I'm warning you now, anything that has the word law in it, anything that's a whole chapter's named after, or anything a whole subsection's named after, you should probably commit it to memory verbatim just in case. So to date, since you guys have already had 241 and you're taking 242, I would say that means that you should, as a bare minimum, know the first Newton's first law of motion, Newton's second law of motion, Newton's third law of motion. That means you know it and you know which one's which. You should also know Kepler's first law of planetary motion, Kepler's second law of planetary motion, Kepler's third law of planetary motion, Newton's law of gravity, Kirchhoff's loop rule, and Kirchhoff's junction rule is something that we'll learn this semester. We'll also learn this semester the zeroth law of thermodynamics, the first law of thermodynamics, the second law of thermodynamics, and the third law of thermodynamics. All of those things you should know. So just keep that in mind. Section 4 is on thermal expansion. Section 5 is on thermal stresses, which is super interesting, but that's normally handled by your engineering classes, so we normally skip that. And that's often the case with my class. When we get to a subsection that has an asterisk next to the subsection, then we might not cover that because it is an optional subsection. Subsection 6, the gas law and absolute temperature. I normally don't cover that in as much detail because what I've found is the vast majority of students have already had chemistry or physics at the high school or college level, and therefore have already covered some uh, ideal gas law problems. But please let me know if you're a student in here that's never covered the ideal gas laws. Let me know so I can make sure I give it a little more time. And not only that, if I don't give it enough time, make sure you contact me and ask me questions so that I can further help you with the ideal gas law. Section 7 is the ideal gas law. Section 8 is problem solving with the ideal gas law. The biggest thing I will tell you in the ideal gas law is one, you can't use gauge pressure, you have to use absolute pressure. And two, you can't use Celsius or Fahrenheit temperature, you have to use Kelvin or Rankine temperature. And I don't cover Rankine, so you have to use Kelvin. We mention it, is all we really do. Finally, subsection 17.9 is the ideal gas law in terms of molecules with Avogadro's number in it, and 17.10 is another optional subsection that I won't be covering. Let me change the name of this file real quick so I can get started on covering your notes. It should be PHY242, and it should be 005B. And today is the 13th of January. So now I have it, and I just recalled that this does not work. Oh well, I just leave it be. At the top of this page, it'll have the wrong email address or the wrong address for my YouTube channel. That's the only downside. So let me go ahead and stop sharing this. Actually, before I stop sharing this, I want to go to another screen uh, that I think I have right here. Here it is. So, is everybody seeing the Feynman lectures, uh, a text document right now? I think you are. So, this is a quote by Richard Feynman. Richard Feynman was one of the people at the Manhattan Project, but he literally was like 16 years old, 16 or 17. He had already finished his bachelor's and was working on his PhD at Princeton. And John Archibald Wheeler, who was his PhD advisor, was part of the Manhattan Project and put him on it, and for good reason. Was a brilliant person. But anyways, here's the quote that I think helps us most regarding the atomic theory of matter. It says, "If in some cataclysm all of scientific knowledge were to be destroyed and only one sentence passed on to the next generation of creatures, what statement would contain the most information in the fewest words? I believe it is the atomic hypothesis or the atomic fact or whatever you wish to call it that all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they're uh, little distance apart, but repelling upon being squeezed into one another. And in that one sentence, you will see there is an enormous amount of information about the world if just a little imagination and thinking are applied." So this is by Richard P. Feynman from Atoms in Motion, from Feynman Lectures on Physics, and there's a link to it. But that's something I wanted to point out to you because that's the way we're going to start off this course with this chapter. So now let me go ahead and open up my iPad screen for you guys. And again, remember the document at the top uh, shows an errant address for my YouTube channel. Whoa, Nelly, did not expect to do that. Oh, there it is. Let's see. All right. So it should pop up any minute now. There you go. So notice my address used to be Billy Younger Physics Solutions. I've now changed that to the at symbol and then Physics Solutions dot com, like that. So that's the only difference, is just from that slash mark over, it should be those purple letters instead of what's at the actual top. I'll have it corrected for future ones, but the main thing is I just want to make sure you guys knew that. Now, what we're going to go into is I'm going to start off by talking to you about atoms and molecules. Now, it's a little different, but we basically have a idea that was given to us in ancient Greece by Democritus. Democritus imagined, let me stop sharing this for a second. Democritus imagined that if you took a chunk of material, now, for us, because we're modern people and we've heard of the periodic table and stuff like that, hopefully you already know this, but the periodic table has elements on it. The first one being hydrogen, the second one being helium, then lithium, beryllium, so on and so forth. They're in a very specific order and they're stacked up in a very specific pattern that is extremely useful. For instance, if you want to find out what you could substitute for a particular element, you can look at any column that that element's in and go above the element that you have or below the element that you have, and you'd be pretty certain that that particular element that you've now chosen will behave chemically just like the element that you were talking about. So, for instance, if you wanted to use carbon, you would notice that immediately below carbon is the element silicon, and that's why people talk about silicon-based life, specifically the physics, or excuse me, the chemistry of carbon is essentially very similar to the chemistry of silicon. So you could, in principle, imagine that. Not only that, a terrible thing, for instance, happened when Madame Curie had discovered radium. Uh, we found out that it glowed. That was pretty impressive. So one of the things that industry came up with was the ability to take the radium that she had discovered and mix that into a paint, and then you could actually paint the little hash marks on your watch face so that at the nighttime you could see it because it glowed in the dark. Well, as terrible luck would have it, this was going on during World War. Actually, I think that was World War II. Yeah, pretty sure it was World War II. Could have been World War One because Madame Curie was a little bit before that, but I'm pretty confident it was World War II. But anyways, all the men were away, and the people that worked factories were, of course, the women that were left behind, and therefore we had a bunch of very young women working in paint factories, painting the dials on watches. And whenever you run into a paintbrush that's getting kind of bristly at the end, one of the common things you do is lick it. And that brings it to a nice little point. Well, that's what they were doing. The problem was they were finding these women that were like 22, 23, 24 years of age, and they had the bone density of like a 80-year-old. And not only that, they eventually got so bad that they were glowing in the dark. But what we discovered happened was they were actually licking their brush like that, and the brush had radium in it, and they didn't know at the time that radium was actually deadly. They didn't know it was poisonous. Radioactivity could cause cancer and stuff like that. So they didn't know that. And what happens is because radium is in the same column of the periodic table with calcium, then your body misinterprets radium as calcium, and all the calcium that you're supposed to get to be bonding as bone in their bodies was actually being replaced by radium. And radium, being further down on the periodic table, doesn't have quite as much strength, bonding strength, as calcium does. So their bones became really weak, and they ended up dying terrible lives, as did Madame Curie. So that's just some idea of the importance of the periodic table and how it works. I've given you a couple cases there already, but the main thing is when you're talking about an element, then the smallest part of that element that still acts like that element is the atom. And as modern people, we also know that there's something called compounds. And the smallest part of a compound that still acts like that compound is called the molecule. So in this ancient Greek time, they didn't have that knowledge, but all they understood was something really small that they couldn't break apart. So here was what Democritus hypothesized. He said he imagined, and for us, since we know about elements and compounds, we're going to imagine him taking, instead of just a rock, which is what he might have said, imagine him taking a chunk of aluminum. You know, maybe he happened to find one of the one pieces of rock that was aluminum, and all of it's been knocked away except for the aluminum. If that's the case, then we can go on. So let's pretend for a second that Democritus did this. And now Democritus said, if I take that block and I cut it in half, and then I take one of those halves and I cut that in half, and I take one of those halves and I cut that in half, and I keep doing this, then one of two things is going to happen. Either one, I can do that forever, or two, I'm going to do that until I get to a point that I can't break it up anymore. And the first one made no sense. He couldn't imagine a scenario in which you could completely cut something in half forever and never, ever, ever run out of stuff to cut in half. So he went with the idea that the other option was true, which was that there was a smallest part of that chunk of aluminum that was indivisible. And the word for divisible in ancient Greek was tom, and the prefix that you'd put on a word to negate it was a. So he called this smallest body an atom, which means indivisible. So that was the initial idea of how an atom might exist or whatever. And then they looked for things that would contradict his hypothesis or maybe support his hypothesis. And one of the things they discovered was, well, when you're walking through the streets of Rome, for instance, you often will smell, fresh bread breaking. I imagine if you were in ancient Rome, you'd smell a lot of other worse things too, especially given what they used for their toilet system and for their laundry system. But the main thing is, if you were smelling bread, he hypothesized that that bread smell that you got was what we now call molecules, but what he would have called atoms of bread that had broken loose and were carried away by the air. And then you walk through them, and those atoms of bread would go into your nose, and you would smell it. And that is actually a fairly correct position, even though it's not atoms. It's actually certain molecules that have certain smells. And yeah, that's the way you smell them, is molecules that have that smell enter your nose. So yeah, you can think about all the horrible things that you've smelt and what that means on your own time. So this idea of the atom was specifically that ultimately the atom, which I said is the smallest part of an element, and the molecule, which I said is the smallest part of a compound like water, for instance, or ammonia or sucrose or one of those type things, their smallest part is a molecule. Now, when we say their smallest part, we actually know with modern science that we've been able to break the atom apart in some ways easily. For instance, when you just walk across the carpet and scuff your feet on it, you're actually stripping electrons off of atoms, and that's why you become charged. And in fact, you can take a balloon and rub it on your head and then hold it up near a wall, and it'll actually stick to the wall, not because your hair is so greasy that it got some smudge on there that stuck to the wall, but specifically because you rubbed it on your hair. The rubber in the or the latex or whatever the material is that makes the balloon has a larger affinity for electrons than does your hair, if you have hair. Uh, and because of that, it steals the actual electrons off the atoms in your hair, and therefore the balloon becomes a net negatively charged. Now, there could be, in principle, certain types of hair that might actually be more strong than the actual rubber material, in which case the balloon would become positively charged. But the main thing is it's going to become charged, and then when you bring it near a wall, it can actually induce the opposite charge in the wall, and unlike charges attract, so it will actually stick to it. Uh, but that is a simple way of quote unquote breaking an atom, but you're not breaking the atom in the big sense. You're just taking off electrons, which is pretty easy. You can even see it if you take those flavor crystals in Lifesavers and you turn the light off in your bathroom and close the door and start chewing them. You'll see little sparks pop off. That too is reminiscent of the actual electrons either changing orbitals or completely being released from their atom. So when he actually talks about being indivisible, when we say atom or molecule, they're not technically indivisible, but what happens is if you take those electrons off the atom, nothing happens. For instance, hydrogen with one electron is hydrogen, and if you take that electron off, it'll still bond like hydrogen. If you add that electron back and then add an extra electron, it'll still bond like hydrogen. But if you want to actually change something so that it doesn't act like itself, then you have to go to the nucleus. And we have been able to do that. It turns out the periodic table is in order of increasing atomic number, which is a number of protons. And since atoms are normally neutral, the number of protons is equal to the number of electrons. But the atomic number really means the number of protons. And it turns out that that's really what matters in terms of how elements and compounds behave chemically is their orbital radii, if you will, again, allowing for the idea that quantum mechanics says there's not really a radius for that. But either way, that orbital radius and the different distances that our electrons are from the nucleus of the atom is almost completely dictated by the number of protons in the nucleus, not the number of neutrons, not the number of electrons outside of it, but specifically the number of protons. And any element with one proton is going to behave just like hydrogen. Any element with two protons is going to behave just like helium, and any element with three protons is going to behave just like lithium. Now, we have been able to break the atom apart, but the difference is when you break the atom apart, it no longer behaves as the element it was. So, for instance, if you take a uranium atom and break into its nucleus and break it apart, you're going to have two pieces. One piece is going to act like one element, the other piece is going to act like another element, and neither of those elements are uranium. Okay. Similarly, if you have the smallest part of a compound like water or ammonia or sucrose or whatever, if you have that smallest part, you can still break it apart. You can obviously, break off the little Mickey Mouse ears from the water molecule. Remember, the water molecule is basically a big oxygen with a little hydrogen for like a Mickey Mouse ear and another little hydrogen for a Mickey Mouse ear over there. You could easily break off Mickey's ears or ear, and what you have then is hydrogen and oxygen, neither of which behave like water, but you still have something. So it's not that you completely destroyed it by cutting it in half. It just means that no longer it has the properties that it did. And then a higher level above compounds, of course, is just a mixture, which not is not really studied within the physics world very much, except for some very niche types of subjects. So that is our modern picture of the atom. And what we figured out over time is that the atoms are constantly in motion. We've later learned in quantum mechanics that they can't more or less come to a stop. It's really problematic for them to have zero energy, so they don't. But they do jiggle. And what we've discovered is that they jiggle in direct response to temperature. So the higher the temperature the element is, the faster the jiggling goes on. And if you bring it up hotter still, it'll go faster still. Not only that, we've also figured out, for instance, that there's at least three states of matter: solid, liquid, and gas. The only way we could make sense of the atoms behaving like they do in a solid, because a solid has a fixed shape and a fixed volume, the only way we could picture that is if the individual atoms were sort of like balls on a chain link fence. So if you imagine a chain link fence, everywhere the chain link ran across each other, you could put an atom on that. And then up here where there's another one, there's another atom. And then up here where there's another one, there's another atom. And you can imagine just a whole two-dimensional sheet of atoms like that. And that's sort of how the atoms are oriented in two dimensions. Now, if you take and imagine another chain link fence just a little different distance away from that first chain link fence, but also parallel to it, and sort of lined up in some sense with the other atoms so that there's a small distance between one atom in one fence and another atom in another fence, then you're starting to get the three-dimensional picture of what we call the lattice, Lattice. That lattice is the way that atoms orient themselves with respect to each other in a solid. Now remember, they can't stop moving, so they're doing like this, but they're being held apart by some finite distance, and that's like Feynman said, they're being held apart because if they bring them too close together, they repel, but also if you start to bring them too far apart, they actually have an attractive quality to one another as well. So they have some sort of equilibrium distance between them where they're comfortable. and they just sit here and jiggle like this, and that means they jiggle forward and backwards. That's one dimension. They do jiggle left and right. That's another dimension. They jiggle up and down. That's a third dimension, and they just constantly jiggle like that. There's other motions they can make, but not necessarily in the solid state, but still they jiggle like that. Now, if you imagine the temperature getting hotter and hotter, then that jiggling is going to become faster and faster, and you could probably figure out that the equilibrium distance between them is no longer going to be the same as it was in the low temperature. In fact, you're going to expect, because they're moving so fast, they're going to actually separate. So the two atoms that were this far apart at, say, 20 degrees Celsius, if you amp it up to, say, 80 degrees Celsius, maybe they're more comfortable at this distance apart. And that just seems reasonable. And lo and behold, that's exactly what we discovered in nature. Specifically, we discovered that the length, the width, and the height of a solid object increases as the temperature increases. And you could take a linear approach to estimating a formula for this. And it turns out that linear approximation works pretty well for a large range of temperatures. If you go to too large of a range of temperatures, then you're going to have to do some other stuff. But the main thing is we've now discovered, just from the idea of the existence of atoms and the fact that they move, we've discovered that substances generally expand upon getting hotter and contract upon getting smaller. So we've already done something. That's pretty impressive. Uh, Now that I've given you sort of that intro, well, actually, let me go ahead and talk about liquids and gases too. So, as I said, the liquids or the atoms or molecules are stuck in a lattice. So you might imagine this as being like one unit cell, if you will, of a lattice. So you could imagine there's an atom here, 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 and an atom here. At each of these corners of this Rubik's Cube, there's an atom. And then right next to that, there's another Rubik's Cube that has these atoms right here, and then another one that has these atoms right here, and then another one in front of it that has these atoms. And you can sort of picture that. And that is actually one of the fundamental shapes of lattices that we find in nature's. Other ones have the atoms at the corners, but then also an atom in the very center of the Rubik's Cube. Other ones have the atoms at the corners, but also the other ones have the atoms in the center of the faces. So you could have an atom here, 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 and an atom here over here on this side, right? So those are all the different sort of shapes. But as you can imagine, if you keep bringing the temperature higher and higher, the equilibrium distance between the adjacent atoms gets bigger and bigger and bigger, till at some point you're going to get so far apart that they don't have enough strength to keep them next to each other. So this atom that really liked to be really close to this atom, and this atom that really liked to be close to this atom, pretty much stayed next to each other. Not only that, over here there's another atom that this one stayed close to, and over here there's another atom that this one stayed close to, and back here there's another atom that this one stayed close to, and back here's another atom that this one stayed close to, and the same thing above and below. So they pretty much stayed pinned in between their most near neighbors in the solid state. But as you bring that temperature higher and higher and higher, that equilibrium distance gets bigger and bigger and bigger. Eventually, it's probably going to get big enough where there's not enough strength to hold it together and it breaks apart. In that case, what's happened is we're starting to transition from the solid state to the liquid state, and the atoms, instead of having like the same neighborhood of atoms around it all the time, they have a single or a couple atoms that are around it for a long period of time on the microscopic scale. But eventually, they're going to move on to another one. And when I say a long period of time on the atomic scale, we might mean like microseconds. So maybe it spends a whole microsecond right next to this one molecule or one atom. So it's sort of rolling around it like this. But then if you wait after 2 microseconds, say, then it'll accidentally got attached to a different atom and start rolling around that one, and so on and so forth. That's what actually happens in transitioning from the solid state by heating it up, heating it up, heating it up, or decreasing pressure, decreasing pressure, decreasing pressure. It ultimately breaks loose, and then these two atoms that were forever friends when they're in their solid state, they're only part-time friends. And then this one goes over here and starts hanging around another one, and then it goes to yet another one, and then goes to yet another one. But they still stay constantly against each other because the nature of a liquid is that it has a fixed volume, but not a fixed shape. And you can make sense of a fixed volume if the atoms sort of stay touching each other. Now, if you continue further, these atoms are rolling across each other, but they're also still doing that vibrating thing as they're rolling across each other. So if you keep heating it up further and further and further, this big distance where they're rolling across each other gets bigger and bigger and bigger until they can't even hold on to each other for even a microsecond. So they break completely loose and they have no allegiance to any particular atom, and the distance between them relative to their actual diameters is on the order of 10, 50, 100, or something like that. So you now see that they're super far apart, and what we have is a substance in the gaseous state. The atoms are free to move. They're only going to do the only thing they're going to do is they're going to vibrate and move really fast in the x direction, really fast in the y direction, really fast in the z direction, and they're going to bounce off of each other and bounce off of the other molecules that hold it in the container. And lo and behold, now we can understand why gases do not have a fixed volume or a fixed shape. The fixed shape, obviously, we already handled that with the liquid state, but the fixed volume is that they can be huge distances apart, and then you can compress them to they're very close distances together. So that's enough on that. Now let me go ahead and share my iPad screen like we were trying to do so I can introduce you to some of the physics we're going to learn in this chapter. Uh, so I'm getting ready to turn that on. Let's see. Okay, I don't know what it's doing, but all of a sudden my iPad's being a pain in the rear end. Let's see if I can get it now. You'll need to unlock. Okay, there we go. Might have been doing a little spastic thing. Okay, so now we're back in my iPad, and as I said, we're covering chapter 17, temperature, thermal expansion, and the ideal gas law. So the first thing we talk about in the chapter is, well, one thing, let me remind you, there's a chapter opening question that opens every chapter. Make sure you always answer that. Commit to an answer, make a guess, and then wait to find out the answer as you're reading. That keeps you a little more focused while you're reading, and it allows you the scientific method to be applied to learning. So we found out that pedagogically speaking, that is actually beneficial for you to, sort of put your money down on a guess and then wait and find out what the real answer is. Alexander asked, and yes, it should be, this video is being recorded. I'm glad you asked me about that. Plus, I want to double check now. Yeah, it is being recorded. So, anyways, let's go on. I'm discussing. Dang it, the stupid thing keeps getting in my way. Okay, everything keeps getting in my way. There it is, finally. So, as I was telling you, the chapter opening question is something you should answer, and it has the answer in, I think it's at the end of the chapter. But we're going to start off with looking, for instance, at the periodic table. If you look at a periodic table, you'll notice that hydrogen has a mass of about 1. It's like 1.00267 or something like that. And then helium, the second element, has a mass of like 2.02, or and then so on and so forth, each of them. And when you get to carbon, for instance, it's got a mass of around 12.011. Uh, what we tried to do was come up with a unit of mass for atoms and molecules and things like that that wasn't so big, because The gram is used in mass, and that's so small that we ended up switching from the CGS system to the MKS system, where we were using kilograms instead of grams because grams is such a small unit of mass. But gram is a huge unit of mass when you compare it to an atom. In fact, it turns out to be on the order of 10 to the negative 24th grams is the mass of an atom. So what was done to come up with this mass is they said, okay, well, we have this idea where basically if you read the masses on the periodic table, like you would in your chemistry class, you would see that carbon, for instance, has a mass of 12.011. And in chemistry class, we've been taught to read that as grams per mole. So what that means is anytime you have a collection of pure carbon, you can take that pure carbon and weigh it in grams or kilograms, preferably grams. And once you have the mass in grams, then you can divide it by the 12.011. And what that answer is the number of moles of carbon you have. Similarly, if you did that with hydrogen gas, you divide it by 1.002, and that would give you the number of moles that that particular sample of hydrogen had in it. And what a mole is a very specific number of atoms. Specifically, that number of atoms is called Avogadro's number, and it's 6.022 times 10 to the 23rd, roughly. Okay. We actually know it to a lot more digits, but 6.022 is enough here. So that is one way of looking at the masses on the periodic table. I should also point out that those masses on the periodic table are actually weighted averages of all the different isotopes. So you've probably heard of something called carbon 14. That's what we use for carbon dating. And what that means is there's an atomic number for carbon, which is 6, just like the atomic number for hydrogen is 1, the atomic number for helium is 2, lithium is 3, beryllium is 4, so on and so forth, boron, carbon, so on and so forth. But there's also a number called the atomic mass unit, which is, or excuse me, the atomic mass number, which is the total count of nucleons. Meaning, if you counted the total number of protons and neutrons in a nucleus, you would get the atomic mass number. So when you say carbon 14, by saying carbon, you know the number of protons is 6, and by saying 14, you know the total number of protons plus neutrons is 14. If you subtract the 6 from 14, you get 8. So you see that carbon 14 actually has 8 neutrons and 6 protons, whereas the most abundant carbon that exists is carbon 12, and that has 6 protons and 6 neutrons. So when you look at that weight, 12.011 grams per mole for carbon, what that really is you take the percentage of naturally occurring carbon that we find on planet Earth, and you say, what percent of this carbon is carbon 12? And it's like 99.5% or something, say. So you take 0.995 and you multiply it by the mass of carbon, which for carbon 12, we're going to call that 12.000 to an infinite number of decimal places. So we're going to do 0.995 times 12.000 with a bar over it. Now, we might find that carbon 13 is 0.2%. So then we're going to multiply 0.002 times the mass of carbon 13. And we might find that carbon 14 is 0.001%. So we're going to multiply 0.001 or excuse me, yeah, 0.00 or 0.1%, which would be 0.001. We're going to multiply that by the mass of the carbon 14 isotope. And we're going to do that for all the isotopes that are available. And then we'll divide all that by 1, and that'll give us that 12.011 number, just so you know that's where that came from. Now, back up from that for a second, and we're going to go back to the idea of making up a mass for carbon. And I'm sorry that this is all more or less me talking as opposed to me solving physics problems, but it's probably the single most important chapter for understanding what's going to happen for the next 4 chapters. So, and even later than that. So I've really got to explain all this stuff. So their idea was this: hey, we see that carbon 12 is really close to 12 already, and it's so close to 12 that our technology won't even allow us to define how far away it is from 12. So let's go ahead and claim that to be 12 in this new system of units that we're going to come up with. So they said, all right, carbon 12, meaning isotope of carbon 12, has a unified atomic mass unit mass of 12 U. The lowercase u is the symbol we're using here, and it's called the unified atomic mass unit. So carbon 12 has a mass of 12.000000 going on for infinity. Now, when you define that, you can see it's sort of like you're taking the actual atomic mass number and saying that is really equal to the actual unified atomic mass unit because 12 was equal to 12. Well, if you look at it that way, then you can say, okay, well, hydrogen is an element that has a unified atomic mass unit of 1. So if I wanted to know what the mass of a single hydrogen atom would be, then I could take the 1.000 grams that it weighs and realize that that's 1 gram per mole. So if I divide that 1 gram of hydrogen by Avogadro's number, then that'll give me the actual mass of a single hydrogen atom. So if you do that, looking at this piece of paper now that I've got written here, you're going to say let's put it on a pen instead of a eraser. So we're going to say 1 unified atomic mass unit is going to be equal to 1 divided by Avogadro's number. And lo and behold, you're going to find out that's exactly what the conversion factor is. So when you do this, you're going to take 1 and divide it by 6.022 times 10 to the 23rd. And they usually use units of reciprocal mole. So that would be interpreted as mole to the -1 power. And when you do this, you get the answer is 1.6605. Now, I only used 4 sig figs when I wrote 6.022, but I'm giving you the answer with 5 sig figs as if I really had put in the Avogadro's number to 5 sig figs. So it's 1.6605 times 10 to the -24th. And remember, we were measuring that in grams because the mass of hydrogen is 1 gram per mole, and we divided that by 1 Avogadro's number. So we ended up getting the number of grams a single atom of hydrogen weighs. So we'll put that as 1.6605 times 10 to the -24th grams. And therefore, we can realize that the unified atomic mass number, and actually, I shouldn't say number there, unified atomic mass unit is equal to 1.6605 times 10 to the -27 kilograms. So I introduce it that way so you realize, hey, this isn't another constant I got to memorize. I just remember it's 1 over Avogadro's number, which I already memorized. Now, not only does that help us, because now we have an entirely new interpretation of the periodic table. The periodic table used to have 1.00272 or whatever for the mass of hydrogen, and we read that as 1.00272 grams per mole. But because it was done this way, it now also means 1.002 is the mass in unified atomic mass units of the average hydrogen atom. Now, again, because it's 12.002, it's because they combined all those isotopes. Regular hydrogen, of course, is hydrogen 1, and that's just a proton with a neutron, I mean, with an electron. Deuterium is hydrogen 2, that has 1 neutron and 1 proton, and of course, an electron. And then tritium is hydrogen 3, and that has 2 neutrons and 1 proton, and of course, 1 electron as well. So using this idea to make the mass of carbon be exactly 12 allowed us to get a exactly the same numbers as the periodic table gives us, but instead of it being interpreted as grams per mole, it's interpreted as U per atom. So now those atomic mass numbers or atomic mass units that you see on the periodic table can be interpreted as grams per mole, or they can be interpreted as unified atomic mass units per atom. And if you make a molecule, then it's unified atomic mass units per molecule. So now with that, we can actually use this to determine something kind of nice, and that means example 17.1. So we're going to do example 17-1, which is an estimate problem. And I will read these to you. I generally stick in this chapter or in this course, I generally stick to the examples in the book and I pull them up in electronic format. So if you're on your computer and you have the ebook next to you, it's a good thing to have it open so you can look at the examples. But if you don't, it's okay because I'm going to read it to you and I can repeat it if you need. But the main thing is I'm going to read it to you. So here's example 17.1, estimate. The distance between atoms is sort of like the title. It says the density of copper is 8.9 times 10 to the third kilograms per cubic meter, and each copper atom has a mass of 63 U. Estimate the average distance between the centers of neighboring copper atoms. So let me read that again. The density of copper is 8.9 times 10 to the third kilograms per cubic meter, and each copper atom has a mass of 63 U atomic mass units. Estimate the average distance between the centers of neighboring copper atoms. So let me write down the numbers they gave us. There's the Greek symbol U, rho, RHO is how that's spelled. And you can get that by typing R in Microsoft Word and then highlighting it and changing the font to symbol. So if you want to see what that looks like, that's what it is. And this is the density of copper, and rho is the symbol we use for it. And it's 8.9 times 10 to the third kilograms per cubic meter. Now remember, just to give you some perspective, the density of water is 1.000 times 10 to the third kilograms per cubic meter. So copper is about 8.9 times more dense. We're also given that the atomic mass of copper is about 63 U. When you look it up, it's actually going to be about 63.5 something, so it technically should round up to 64, but they're just giving you a rough estimate here. And what they want to know is the distance between the atoms. So distance, oops. So distance between the atom centers. So, what I'm going to do is give you a way of thinking through this process. So, we can imagine, for instance, a big chunk of copper, and that big chunk of copper might make a perfect cube. And in fact, what I'm going to do is force it to make a perfect cube. And what I mean by a perfect cube, oops, sorry, what I mean by a perfect cube is that it's actually going to have the same dimensions left and right as it does up and down, as it does forward and backwards. So this distance from here to here is 1.00 meters. This distance from here to here is 1.00 meters. And this distance from here to here is 1.00 meters. So that means the volume of this chunk of copper is 1 cubic meter. Therefore, the mass of the cube, actually, let me write that in a lowercase m. The mass of the cube is equal to 8.9 times 10 to the third kilograms. Does anybody not know how I know that? Okay. Well, a former high school teacher told me that they use this little mnemonic in high school to teach students about density, and it's a little heart with a line through it. That is actually pretty helpful, so that's why I show it to you. The formula for density is equal to mass over volume. So if you want to know the mass, you have to multiply the density times the volume. So if I take the volume of this metal, which is 1 meter times 1 meter times 1 meter, you get 1 cubic meter. And if I multiply 1 cubic meter by 8.9 times 10 to the third kilograms per cubic meter, the cubic meters cancel out, and I'm just left with 8.9 times 10 to the third kilograms. So that is the actual mass of that. Now, since I actually made this copper cube, actual cube, it's not unreasonable for us to assume that the number of atoms that are running from left to right is exactly the same as the number of atoms that's running from front to back along that 1 meter length. And that's exactly the same as the number of atoms that are running from bottom to top along that cube. So that's sort of our idea is we're going to think that each of these sides have a specific number of atoms lined up along it. And in this case, I'm going to say the number of atoms is going to be n star, and the number of atoms here is going to be n star, and the number of atoms here is going to be n star, so that n, the total number of copper atoms, is equal to n star cubed. Okay? That should make sense. It's just like your old multiplication tables. If you had, 10 rows by 10 columns, that meant you had 100 individual squares. If you up that to 3 dimensions and you have 10 rows, 10 columns, and then 10 layers, it's 10 times 10 times 10, so you get 1,000. That's what's happening here. So the total number of atoms here is n cubed, which is actually equal to, or n star cubed, which is actually equal to n. So if I want to know exactly how many atoms n star is, then all I have to do is assume that the mass, 8.9 times 10 to the third kilograms, is the mass of n, not n star, but n copper atoms. And n copper atoms, of course, weigh 63 unified atomic mass units. So the mass of the block of the cube, actually, I remember I wrote that in a small, uh, as a small m. So the m of the cube, which is equal to 8.9 times 10 to the third kilograms, is also equal to the atomic mass unit for copper times N. That means that N is going to be equal to 8.9 times 10 to the third kilograms divided by 63 unified atomic mass units, because that's what this quantity is. Okay. But that doesn't make any sense because I've got kilograms in the top and I've got unified atomic mass units in the bottom. So I need to convert that unified atomic mass units to kilograms, in which case I'm going to say there is 1.6605 times 10 to the negative 27 kilograms per one atomic mass unit, unified atomic mass unit. So now I can find out what exactly N is. So if I take the 8.9 times 10 to the third, and I divide it by 63 times 1.6605 times 10 to the negative 27. And I put these in parentheses, by the way. That's especially with some cheap calculators I've found. When you do scientific notation and you divide by a number with scientific notation, some of the cheap calculators I've found will actually separate the times 10 to the part from the original number and put it in the numerator, so that would screw everything up. So be careful, make sure you do that correctly. When I did do this, I got 8.508 times 10 to the times 10 to the 28th as the total number of atoms of copper. Because that's the total number of atoms of copper, I can take the cube root of it, and that'll give me the number of atoms that are spread apart along the horizontal line, or spread apart across the vertical side, or spread apart across the in and out side. So that means N star is equal to the cube root of 8.508 times 10 to the 28th. Now, I should point out that really I only had two sig figs, so the 0 and the 8 were not sig figs. And the reason I had two sig figs was they gave us the density as 8.9 times 10 to the third, and they gave us the atomic mass of a copper atom as 63. So that's literally only two sig figs. So now I can take the cube root of this number, and to take the cube root, you can actually just raise it to the 0.3333333 power, because 1/3 is the exponent that's equivalent to a cube root. And for that number, I get 4.40. That's one extra sig fig too, and that's times 10 to the 1, 2, 3, 4, 5, 6 times 10 to the 9. So that means there's 4.4 times 10 to the 9 atoms, or you could say 4.4 times 10 to the 9 columns of atoms in the front face, and 4.4 times 10 to the 9 rows of copper atoms on the front face, and so on and so forth. Now, if you think about this, so let's imagine that we have one atom and then its natural space between it and another atom, and then its natural space between it and another atom, and so on and so forth. If we just had, for instance, four atoms, then what you'd see is that the distance for four atoms is really three times the distance of separation. So for four atoms, the row is only three times as long as their separation. So what that means is if you have n atoms, then there's n minus 1 spaces between them. So if you take that whole distance and divide it by n minus 1, that'll give you the distance between each of them. So I'm going to take the whole distance of 1 meter and divide it by n minus 1. But guess what? 4.40 times 10 to the ninth minus 1 is still 4.40 times 10 to the ninth. So now I'm going to say the distance, which we're going to call d, is equal to, the distance, which we're calling d, is equal to 1.00 meters divided by 4.40 times 10 to the 9. And that gives us 1 divided by, I'm just going to choose my answer, and I get 2.3 times 10 to the negative 10th. So that is the separation distance between the center of one atom and the center of another atom in copper, specifically at right 20 degrees Celsius, because when you look up the density of a material, the density is different depending on the temperature. Like we said, the actual atoms get farther and farther apart for a lot larger temperatures. So you'd expect if you got up to, for instance, instead of 20 degrees Celsius, you looked at the density of copper at 40 degrees Celsius, you'd probably find that it'd be smaller than 8.9 times 10 to the third kilograms. So in this case, what we just discovered was the separation between them is about 2.3 times 10 to the negative 10 meters. Now, if you look at that, you'd realize that the distance from the center of one atom to the center of another atom could be thought of as if the atoms were actually pictured as leaning right against each other like this, then you could think of the distance between them as the radius of one atom plus the radius of the other atom. And therefore, some people tend to use this figure, the 2.3 times 10 to the negative 10th meters, as the actual diameter of a single molecule. Okay, or excuse me, a single atom. All right, so that was example 17, 1. And now what I'd like to do is motivate the formula we're going to use for expansion and contraction due to temperature. So what you might argue is that the change in length, when you heat up an object of length L0, the length that it changes by should be directly related to or directly proportional to the original length. So the way we write proportional to is we write that little alpha fish looking thing there. And what we're saying is we expect this is going to be proportional to the original length, which is what we're calling L0. Now, that might not make sense to you, but think about it this way. If you had a 1 inch long chunk of metal and you heated it from 0 degrees Celsius to 50 degrees Celsius, you do expect it's going to increase in length. But if you now took that 1 inch piece and instead of having that, you took a 12-inch piece and you heated that up from 0 degrees Celsius to, 50 degrees Celsius or whatever, you'd expect that 12-inch piece to get markedly longer than the 1 inch piece did. So it does seem somewhat reasonable about that the change in length should be directly proportional to the original length. And that's why I put delta L is proportional to L0. Now, here's the part where we're going to go on the assumption that it's linearly related, meaning the change in length, the L final minus L initial, is not only proportional to the initial length, I'm going to argue that it's also proportional to the change in temperature. And the way we write change in, of course, is that triangle called delta. So we're going to say that we expect that to be the case. Now, we don't have any guarantee of that, but we do know, for instance, with the Maclaurin series and the Taylor series and that sort of stuff, linear is sort of the lowest order approximation. So, as a bare minimum, you would think the first order term would be a linear one. Then you might have some second order terms that would be quadratic and third order times and so on and so forth. But all that it really has to be tested upon is experiment. And experiments showed us that for significantly large chunks of temperatures, they are linearly related. So this equation works fine. Now, the one thing that's different from this, or one thing we've neglected, is if I take a 1 inch long piece of aluminum and heat it up from 0 to 50 degrees Celsius, there's no reason to suspect that a 1 inch long piece of gold heated up from 0 degrees Celsius to 50 degrees Celsius is going to change by the exact same amount. So we might expect that the property of the material is how much it expands, and it's called the linear coefficient of expansion. So we can make this into an actual equation by putting a constant to represent the linear coefficient of expansion and then just another arbitrary constant to make it an equation instead of a proportional to. Or we could just assume that the extra constant would just be absorbed by the linear coefficient of expansion. And that's what we've done in physics. So now to make this an equation, we're going to say delta L is equal to alpha, the linear coefficient of expansion, times L0 times delta t. Now, just to remember, delta L would be L minus L0. Delta t would be t minus t0. Now, with all that, we can now say this is one result, and it's a result that you can use. So by all means, use it. But the way your book is doing it, and the way a lot of people use it, is they go ahead and take the fact that the delta L is L minus L0, and you write it in there like this, and then you can get L, the final length, is equal to L0 plus alpha L0 times delta t, which lends itself quite easily to writing the final length is the initial length times 1 plus alpha delta t, and that is the other version that we use. So there is a table in your book that gives us the linear coefficient of expansion for various elements and compounds, and that table is in chapter 17. It's actually in section 17.4. And for instance, aluminum is equal to 25 times 10 to the negative 6. And the units of that, of course, have to be Celsius degrees to the negative 1 power. If you wanted to look at brass, that turns out to be 19 times 10 to the negative 6 reciprocal Celsius degrees. Here's something kind of neat. Iron or steel, so I'm just going to write it like this. That turns out to be 12 times 10 to the negative 6 Celsius degrees to the negative 1 power. But here's the neat part. Concrete is also equal to 12 times 10 to the negative 6. So this is another one of those cases where the universe left us this nice little gift, specifically the fact that the coefficient of linear expansion of concrete and steel are the same, so that we actually now can make reinforced concrete. Reinforced concrete is made by taking steel and putting it under tension and then pouring concrete around it, allowing the concrete to set, and then that steel inside of the concrete makes the concrete much more strong than it would otherwise be. And since they have roughly the same coefficient of linear expansion, you don't have to worry about it degrading over a short period of time because of the different rates of expansion and contraction. So, anyways, we'll solve some more problems with this next time. The class is over. You guys are free to leave. Make sure you chat at me your first and last name if you haven't already. And like I said, I'll probably be able to post this tonight on my YouTube channel, but feel free to subscribe. You can unsubscribe later, but feel free to subscribe. That way you'll get an email every time I post anything. Have a good one, and I will see you guys Thursday. And I might even, those of you that come, and I might even see you Thursday morning for lab as well. Thank you, Miles. Have a good evening. Thank you, Alexander. Alex, I know who you are. Anybody have any questions? This is the time where I'd normally start my office hour, but no one's come this time, so we're not going to be doing it. But if you have any questions, I can still answer them. Did you have any questions, Miles, or are you not there? I think you're there. You just sent me a message. Yeah, you did. I'm glad you're excited about the class. I hope I can make it fun and not disappointing. All right. Well, I suspect that he dropped or left the class, but it just hasn't registered that he's left yet. So I'm going to go ahead and call it a day. You folks have a good one. Thanks for coming, and I will see you next time. Bye bye.